for having me. I'm really happy to be here to give a talk about real numbers. The title of my presentation is Are Real Numbers Real? And I'm going to answer that question. My approach in this talk is more philosophical rather than mathematical or technical. I thought it's more appropriate for mathematical or technical. I thought it's more appropriate for this workshop. So please don't worry about mathematical and technical proofs or details. I'm not going into details of mathematical proofs or anything. I'm just going to explain some mathematical ideas and facts and theorems about real numbers, and then focus on philosophical aspects of real numbers. Okay, let's start. Before that, I should mention also that the result of this presentation is part of an ongoing research project which I'm collaborating with Professor Mohammad Ardashir, who is my supervisor at Sharif University of Technology, and also my friend Mohsen Shahriari at the same university. Okay, first of all, we need to answer this question: what are real numbers? What is the definition? And what is the motivation? For doing that, we need to develop some arithmetic and algebra. Okay? What we already have is natural numbers and operations and relations between natural numbers. For example, addition, multiplication, and order. All of these objects and operations and relations are primitive. We don't talk about them, we don't define them, we just accept them as primitive objects and notions. For example, when I say 2 plus 2 equals 4, we don't prove it, we don't define it, we just accept it as a primitive fact, as a primitive object, as a primitive statement. This is where we start our mathematics. This is the starting point of our mathematics. And I should now define number system. What is a number system? A number system is a collection of objects with some specific operations and relations, such as addition, multiplication, and order between the elements. These operations and relations must satisfy some certain properties. For example, commutativity, associativity, and distributivity, and so on. Therefore, these operations and relations are not so arbitrary. They must satisfy some certain properties. The first and concrete example of a number system is the structure of natural numbers. Natural numbers is a number system. But there is something wrong with natural numbers. We cannot solve this equation in natural numbers. There is no natural number satisfying this equation. Y plus 2 equals 1. Therefore, we cannot perform subtraction all the time. For example, we cannot subtract 2 from 1. We want to solve this problem. Therefore, we want to extend the natural numbers to a number system such that in that number system, equations like y plus 2 equals 1 has a solution. Therefore, we introduce integers. The definition of integers is this. An integer is an ordered pair, m and n, of natural numbers. Therefore, every integer is an ordered pair of previous objects. We use previous objects, natural numbers, and construct new type of objects, so-called integers. The definition is very legitimate, very acceptable. There is nothing wrong with this definition. Everything is legitimate and acceptable. And we should also define equality between the new elements. When we say that two integers are equal, we should define a relation. we define the equality between the integers as this. The integer a and b is equal to the integer c and d if and only if a plus d equals b plus c. This is the definition of equality between the integers. The example is this. 2 and 3 equals 56 and 57. This is because 2 plus 57 is 59 and 3 plus 56 is also 59 and 59 equals 59 in natural numbers. Therefore, these two integers are equal. And both of them are representing -1 in the language of high school mathematics or ordinary mathematics that we are familiar with. Okay, so we have defined new type of objects, so-called integers, and we defined the equality between the new objects. Now we can also define addition, multiplication, and order between the elements. For instance, I've written the definition of addition. A and B plus C and D equals A plus C and B plus D. This is the definition of addition between integers. For example, the integer 1 and 5 plus 11 and 8 equals 12 and 13. In the language of high school mathematics, the integer -4 plus 3 equals -1. This is compatible with what have we learned in high school and ordinary mathematics. Okay, everything is good and acceptable. And what is the relationship between the natural numbers, previous objects, our primitive objects, and the new type of objects, which is integers? The thing is, we can embed natural numbers into integers. Therefore, for example, every natural number n can be assigned to the integer n and 0. With this embedding, you can extend natural numbers to a bigger number system, which is called integers. And this embedding preserves everything, preserves addition, multiplication, and order on natural numbers. You don't destroy the previous building. For constructing a new type of objects, you have two ways. The first one is to destroy the previous building and construct a bigger new building. But the second way is to preserve the previous building and just construct new floors above of it. And here we have chosen the second way. We don't destroy the previous one. We just extend. This is the meaning of extension in arithmetic. We just extended the natural number system to a bigger number system, which is called integers. Therefore, we can consider natural numbers as a subset of integers, but up to isomorphism. This is not the case that every natural number is an integer. This is true when we add this phrase, up to isomorphism. This is an important thing that sometimes we forget to mention it. Now, our problem has been solved. Equations of this type have a solution in integers. Y plus m equals n, where m and n are integers. Therefore, we can always perform subtraction. Subtraction is always allowed in integers system. But a new problem arises. The equations like 2 times y equals 1 doesn't have any solution in integers. Therefore, we want to extend the integers to a bigger number system such that equations like 2 times y equals 1 has a solution. So we introduce rational numbers. A rational number, the definition is this. A rational number is an ordered pair, m and n, of integers where n is non-zero. Again, every construction is finite, every construction is acceptable. There is nothing wrong with these definitions. And we also need to define the equality between the new elements. When we say that two elements are equal, we say that the rational number a and b equals the rational number c and d if and only if a times d equals b times c. For example, the rational number 1 and 2 equals the rational number minus 6 and minus 12, because 1 times minus 12 is minus 12, and 2 times minus 6 is again minus 12. And minus 12 is equal to minus 12 in the structure of integers. Therefore, these two rational numbers are the same, are equal. We can also define addition, multiplication, and order on rational numbers. For example, I've written the definition of multiplication here. A and b times c and d equals a times c and b times d. For example, 1 and 5 times minus 3 and 8 equals minus 3 and 40. This is also compatible with what we have learned in high school and ordinary mathematics. Again, the relationship between integers and rational numbers is this. We can embed integers into rational numbers by this assignment. The integer z is assigned to the rational number z and 1. And this embedding is again preserves addition, multiplication, and order of integers. We don't destroy anything. We just extend the previous building into a bigger building. And again, we can consider integers as a subset of rational numbers, but up to isomorphism. And our problem has been solved again. Equations of this type, m times y equals n, where m and n are rational numbers and m is non-zero, has a solution in rational numbers all the time. Therefore, besides subtraction, we can always perform division as well, except by 0. So, rational numbers form a very good number system. All 4 famous operations are allowed: addition, subtraction, multiplication, and division except by 0. Such a number system is called a number field. The notion of field is the notion of abstract algebra, but here, because we are focusing on number systems, we call it a number field rather than field. But the problem still remains. This equation, y to the 2 equals 2, doesn't have any solution in rational numbers. In high school, teachers may tell you that because of this phenomenon, because y to the 2 equals 2 doesn't have any solution in rational numbers, we extend rational numbers to a bigger number system, which is called real numbers. But I'm going to tell you that this explanation is misleading. This is not the case. And here we are going to see why and how. Okay, that's enough. We want to solve this problem once and for all. In other words, we want to construct a number system in which every algebraic equation has a solution. Such a number system is called an algebraically closed field. By an algebraic equation, I mean this kind of equation. P of x equals 0, where P of x is a polynomial, is a non-constant polynomial. For example, x to the 3 plus 2, x to the 4 minus 1 equals 0. This is an algebraic equation. If we have a number system such that every algebraic equation has a solution, we say that number system is algebraically closed field. So the question is this: does there exist an algebraically closed field? that is an algebraic extension of the rational numbers. Therefore, what we want is that we want to extend the rational numbers to a bigger number system such that every algebraic equation has a solution. Such a number system is called an algebraic closure of rational numbers. So we can ask this question in another form. Does the system of rational numbers has an algebraic closure or not? The answer is yes. We can construct such a field in a completely constructive and finitary way without using the law of the excluded middle and even without using the axiom of countable choice. I refer you to this paper by Dirk van Dalen and Wim Ruttinger, Constructing Roots, 1986. Therefore, we can do that. We can construct a number system, which is an extension of rational numbers, such that every algebraic equation has a solution in that number system, in a completely finite and constructive way. So our problem is solved. Therefore, why do we need real numbers at all? As we just saw, algebraically speaking, as far as algebra and arithmetic is concerned, real numbers are not needed at all. So when somebody says that because this equation doesn't have any solution in rational numbers, we need to define some sort of number system which is called real numbers, this explanation is misleading, because we can solve this problem in the most sufficient way without referring to any kind of notion such as real numbers. So why do we need real numbers at all? What are real numbers anyway? What is the definition of real numbers? Before answering that question, I should say something about developing of geometry. Geometry is another important branch of mathematics, besides arithmetic and algebra. The primitive notions in geometry are points, lines, segments, congruence, and so on. And the thing is, geometry can be developed independently of arithmetic. We don't need to use the notions of arithmetic and algebra to develop geometry. We can prove important theorems in geometry without depending on arithmetic, without using any theorems in arithmetic and algebra. These two branches of mathematics are completely independent. At least in nature, they are independent. But there is a dream here. The dream is to construct a bridge between geometry and arithmetic. In other words, we want to construct a number system such that every point on the line is assigned to one and only one number. In other words, we want to construct a number system such that the points on the line is in one-to-one correspondence between the numbers. So the question is it possible? And this is the definition of real numbers, actually. The real numbers are a number system which is an extension of rational numbers, and there is a one-to-one correspondence between the points on the line and the numbers. So this is the definition of real numbers, and what we should do is that we should look for real numbers. Can we find real numbers in our previous constructions or not? One important point that we should think about it is this. The real numbers come from geometry. It didn't come from arithmetic or algebra, as we just saw. Because algebraically speaking, we don't need real numbers at all. the definition of real numbers based on the notion of points and lines, which are geometrical notions. So without geometry, there is no such things as real numbers. This is a very important point. So this explanation is misleading again. Okay, we should look for real numbers. What we already have, what the number systems that we already have are natural numbers, integers, and rational numbers. Rational numbers is the most bigger one. So what we should ask is that, are rational numbers real numbers or not? Okay, the answer is no. Rational numbers are not real numbers because there is always a gap between rational numbers. What we want to do is this. We have a number system which is called rational numbers, and we have points on a line. The question is this: can we assign every point on a line to a rational number or not? We assign number 0 to this point, for example, and number 1 to this point, and number 2 to this point, and so on. We assign number -1 to this point, number -2 to this point, -3 to this point, and so on. What about, for example, this point, the middle point? We assign 1/2 to this point. And what about this point, for example? We assign 4/3 to this point, and so on. When we do this and continue this procedure, there are some points on the line that are left without any assignment. For example, consider this point by Pythagoras theorem. This point is length 1. Consider this point. By Pythagoras theorem, we know that this point is not assigned to any rational number. Therefore, there is always a gap between the points. If we assign every point on the line to a rational number, we cannot construct a one-to-one correspondence between points on the line and rational numbers. Therefore, rational numbers are not real numbers, because one important thing about real numbers is that it must be a correspondence between points on the line and real numbers. Okay, we need to fill the gaps. We need to fill the gaps between the rational numbers. So the question is it possible? Can we extend the rational numbers to such a number system? Yes, we can. But in a very unnatural and non-finitary way. This is the most important part of my presentation. How do mathematicians do the job? There are two famous ways. One is Cauchy construction and the other is Dedekind construction. And let's see what is wrong with these constructions. First of all, let's talk about Cauchy real numbers. Every Cauchy real is an infinite sequence of rational numbers. Not a finite pair, not a finite sequence, but an infinite sequence. Therefore, you can see here the difference between the construction of rational numbers from the construction of rational numbers. Every rational number is an ordered pair of integers. Every integer is an ordered pair of naturals. But here, every Cauchy real is an infinite sequence of rational numbers. This is the structure of a rational number. M and N are integers, and this is the structure of a real number. M0, M1, M2, and so on, they are rational numbers. So every individual, every object is an infinite object. This is very unnatural and unacceptable because we cannot do that. You can consider you can take two rational numbers, for example. You can take, for example, two integers, put them together, and construct a new object. We can do that. We can do it on the paper, on our mind, but you cannot do this. You cannot take infinitely many rational numbers and put them together and construct a new object. I don't know where this has come from. This is very unnatural, very unacceptable. And also this is the case in Dedekind real numbers. Every Dedekind real is an infinite set. Again, not a finite set, not a finite pair, but an infinite set. Therefore, in this number system as well, every number is an infinite object, which is again quite bizarre, which is quite unacceptable. For example, let me show how bizarre this is. If x is a real number, for example, Cauchy real number, and y is another Cauchy real number, x must be something like this. And y must be something like this. Okay, x is an infinite object, whatever it means. Y is an infinite object, and we should define addition, multiplication, and order, and many other kinds of operations. For example, how people define the addition, x plus y, this is defined as in this way: x0 plus y0 and x1 plus y1 and x2 plus y2 and so on to the infinity. Therefore, we can never perform an addition in real numbers because you cannot do it in a finite amount of time. Therefore, you can never add up to real numbers in any way. This is quite bizarre in my opinion. For example, the square root of 2 plus the square root of 3. You cannot do this. You just leave it alone. Leave it in this way. This is not the case never in rational numbers, for example. We can always add rational numbers in this way. It can be done. Everything is finite, but here it is not. You just leave it like this. Okay, if we accept these quite bizarre definitions, then the question is, can we feel, are these kind of real numbers, for example, in Cauchy construction or Dedekind construction, are these actually real numbers? Are these actually filling the gaps of rational numbers or not? In some sense, yes, because we can prove a sort of completeness property. The completeness property is this statement: every Cauchy sequence of the real numbers converges to a real number. In the statement, in the setting of Cauchy real numbers, we can say that every Cauchy sequence of Cauchy reals converges to a Cauchy real, and in another setting, every Cauchy sequence of Dedekind reals converges to a Dedekind real. Therefore, we can convince ourselves that these definitions, these constructions of Cauchy construction and Dedekind construction are filling the gaps. Because if you approach to a point by real numbers, that point is again a real number. This is not the case in rational numbers. If you approach to a point by rationals, the point may be not a rational. a rational number. For example, the square root of 2. But this is not the case in Cauchy construction and Dedekind construction. So the problem is solved, but at a very heavy cost. The heavy cost is that we must accept the existence of actually infinite objects. This is the meaning of actual infinity. There is nothing wrong with potential infinity. The natural numbers are infinite. But in what sense? Natural numbers are infinite in this sense. When you give me a natural number, I can give you a bigger natural number. Therefore, the set of natural numbers are not finite. But this is not acceptable that we consider all natural numbers together and consider it as a new object and work with it. This is the meaning of actual infinity. This is what we have done in construction of real numbers. So the question is it possible to construct real numbers in a completely finitary way, so that the resulting objects in this setting, those objects are numbers, are themselves finite? Is it possible to do that? For example, like constructing rational numbers or integers. Can we construct real numbers in such a way, such a finite and complete constructive way? In the following, we present our contributions and we answer this question. What we have done is this. We introduced a minimal set of expected axioms for the real numbers. These axioms are minimal in the sense that every mathematician who are working with real numbers expect the real numbers to satisfy these axioms. For example, everyone expects real numbers to be an extension of rational numbers. Everyone expects real numbers to have some sort of completeness property, and so on. Our axioms are minimal. We don't use any superfluous axiom or anything. The second thing is that these axioms are formulated so that every well-known definition of the real numbers is a model of these axioms. For example, in constructive mathematics, by constructive mathematics, I mean without using the law of excluded middle and axiom of countable choice. There are at least 7, as far as I know, there are at least 7 different definitions of the real numbers. And the thing is, these number systems are not isomorphic to each other. In the classical mathematics, all these definitions are isomorphic, but in constructive mathematics, all these 7 definitions are not isomorphic to each other. And each of them are extending rational numbers and form a completeness. In other words, all of them are filling the gaps of rationals in its own way. This is also an interesting fact. What we have proved is that we have shown that all these 7 known candidates for the real numbers are models of our axioms. Therefore, our axioms are very suitable for axiomatizing the real numbers, constructive real numbers. And our main theorem is this. Let R be a candidate for the real numbers that satisfies our minimal axioms. Therefore, R is a structure which is a number system, which is an extension of rational numbers and a candidate for real numbers and satisfies our minimal axioms. Then what we have proved is this. The equality relation between objects is not decidable. In other words, this statement cannot be proved in a constructive way. You cannot prove this. For all x in R, either x is 0 or not. We cannot prove this statement constructively. We don't know what is the construction of R. We just know that R is a model of our minimal axioms. Whatever is the construction, that the equality is not a decidable property. Therefore, the objects in question, here the elements of R, cannot be constructed in a completely finitary way. Because if everything is finite, if every procedure is completely finite in a finitary way, every mechanism that you have been using to construct new objects is finite, then the decidability of equality must be true. Because, for example, I give you two elements, A and B. Let's suppose that every construction, every procedure to construct new objects of R is finite. Okay? Then you can look at A and look at B and compare them together and decide whether A equals to B or not. You can decide it in a completely finite way and in infinitely many steps. But we proved that we cannot do that if the set R, if the structure R is a model of our minimal axioms. And our minimal axioms are axioms that everyone expects real numbers to satisfy those axioms. So what is the conclusion? The conclusion is this: a finitist mathematician who rejects actually infinite objects may have to give up the dream of establishing a correspondence between geometry and arithmetic. That is, between points on a line and a system of numbers. If you are a finitist mathematician who doesn't believe in actual infinity, you cannot believe in real numbers. Because if you want to have the structure, so-called real numbers, you have to use infinity as a mechanism to construct the objects. You have to use some sort of infinity. Your objects must be infinite in some sense. It cannot be done without using infinity. And using infinity is forbidden for a finitist mathematician. Therefore, the answer to the question, are real numbers real, is negative. Real numbers are not real. They are ideal, actually. So, this is my answer to the question, and I believe that real numbers are not real. Okay? Thank you.
Any questions or comments?
I was wondering about this theoretician, the finitist mathematician, because so he doesn't like to have infinite objects, but then he wants to think about the line in space. But the line, when it's considered to I have this dream of capturing every point on the line, he's thinking of the line as having infinitely many points, no?
I think that it's not true that we think of lines as a collection of infinitely many points.
So
Because
what's the alternative?
the alternative is that you think of a line as a primitive object,
It has infinitely many paths.
and it has points on it, but it's not in the sense that it's not the case that the line is the same. It's exactly the same as points, a collection of points.
Fine, but still has infinitely many points. I understand you want to take it as primitive, but you still grant that it has infinitely many points, or infinitely many sub-segments. No?
Yes, that's a good objection, but I don't know. Because when you say that, for example, when you say that X is an infinite sequence, for example, x0, x1, x2, and so on, you are considering infinitely many things at the same time, okay? I think this cannot be done in arithmetic, but in geometry, I don't know how we can. Yes, I should think about it.
Yeah, thanks. I've just got a sort of suggestion for a different moral that one might draw from your results, given what you're just saying. So it seems like, I mean, one way of thinking about it is like we run into this problem if we try and start with the natural numbers and build up to the real numbers, given certain philosophy of math kind of background assumptions like finitism, some no actually infinite objects and so on. But we're happy to accept the existence of the line in some sense. So I was just thinking, well, maybe the moral we should draw is something like this whole idea of starting with the simpler objects and building up by definition. Maybe that's the wrong way to proceed in that case. What you should do is start with the real line. That's your primitive. And now let's say, also as a primitive, here are our primitive numbers, not the natural numbers, but the real numbers. The real numbers are the ones that correspond to the points on the line. And we're happy to say there's a line, in whatever sense it's infinite. So we say that's our primitive number system, and then we define the rest of the number systems as as subsets, right? As natural numbers are a certain type of real number and so on.
Yes.
And that actually has a nice advantage compared to the standard way in set theory of building up, right? Because as you yourself pointed out, when you build up, you get slightly I don't know if they're slightly or very, you get counterintuitive results like, a natural number actually isn't an integer in some sense, because it's not a subset. One's not a subset of the other, right? You have to do weird stuff like say the natural number is an integer up to isomorphism or some, it's like, whoa, what? I thought natural numbers were special cases of the integers. So maybe starting with the reals and defining downwards would be better. I don't know, what do you think about that strategy for somebody with your collection of assumptions?
I think this is the true historical thing that mathematicians do. Because in history of mathematics, actually, for example, in Euclidean geometry, this is the case that they have defined arithmetic with respect to geometry, and they are trying to define real numbers by lines, by segments. And this is the case in the real history of mathematics. But this is not what I just tell you. This is not the real history of mathematics. This is potential history, for example.
Sure.
This is not, for example, we can think of it as this way. We can think of building natural numbers, assuming natural numbers and building integers and rational numbers up to the natural numbers. But this is also a good point of view. And yes.
Yeah, it just seems like a way of avoiding this harsh conclusion that the real numbers don't exist or something like that, or we can't tell whether they exist.
Yeah, the thing is, we are focusing here on the number system. If we want to have the complete number system with concrete definition of addition, multiplication, order, and objects of the number system, then we have to define it in an arithmetical way.
Sure.
If you want to do that, you have to use some sort of infinity as a mechanism.
Well, but I mean, you got to start with primitives, and the primitive you're starting with here was the natural numbers. So you got to start with some primitives, otherwise your definitions don't get off the ground. So the suggestion would be start with a different primitive, the reals and the lines. Start there.
That's the geometrical.
Yeah, exactly.
If you want to do it in purely arithmetical way, I don't think it cannot.
Yeah,
can
that
be the case.
Absolutely. That's kind of the result of this.
If you want to treat them as different branches of mathematics and treat them purely different in a different way, then it cannot be done.
Yeah.
I think the only way is to think of them as the same thing at the first place.
Yes, that's kind of the suggestion.
Yeah.
But yes, okay.
Yeah.
Yeah, no, I see.
Yeah.
Yeah, yeah. Thanks.
Thank you for.
You mentioned that your minimum axioms can be shown to be compatible with all 7 constructions of real numbers which are not isomorphic. And my question is your axiomatic system then useful for identifying some logical compatibility between different approaches to constructive analysis?
Yes, because this is actually the first motivation that we
Okay.
had. We wanted to prove something in constructive mathematics, constructive analysis, and the question was which real numbers we should consider, because there are 7 different anisomorphic real numbers in constructive mathematics. What we have done is that list these minimal axioms and just prove the theorem for any arbitrary model of these axioms. And we can make sure that all these 7 anisomorphic definitions share this property. And this is the first motivation that we had.
Yeah, does it then motivate some better notions of compatibility that is not isomorphism somehow? Because it seems that if we can somehow naively accept that all these 7 things satisfy what we believe real numbers are to be, even if they're not isomorphic, then is there like better notions that somehow
Yes, this
include all
is
of them?
based on your philosophical ground. For example, if you believe in axiom of countable choice, then some sort of definition is good for you. If you don't believe in, for example, sets as primitive objects, then the Cauchy and infinite sequence are good for you. These 7 non-isomorphic definitions, each of them has its own advantage and disadvantage. If you want to see what definition is good for you, you have to look into philosophical aspects that you can accept.
Okay.
Yeah.
Thank you.
Thank you.
Thank you for your talk.
Thank you.
I'm just curious if you are not also assuming implicitly a view on the existence of mathematical objects, because I was thinking, for instance, on Russell, who says that if you can construct real numbers like through Dedekind cuts or Cauchy sequences, he doesn't have to be committed to their existence. He said, look, this is a kind of logical fiction that is defined, and then they don't really have to exist. Couldn't you have an advantage on that? Because then you have your real numbers, and you still do not have to be committed to them?
Your explanation reminds me of some good analogy here. For example, consider this figure. What is this? We may say that this is a circle, okay? But this is not a circle. This is some points that put them together with a little distance, and this is not a real circle, okay? So the real thing, the real fact is this. But we can see this picture as a circle. We can see this picture as a complete circle, and our mind would complete this picture to see it as a circle. And this is the thing that we are doing in the case of real numbers. The thing is, there is no real number. Everything is rational numbers. But when you want to, for example, when you want to consider the square root of 2, you see this decimal expansion. This is this sequence. and so on. This is again is similar to this thing. There is no such thing such as completed object. Okay? There is no such thing. This is not real. This is not real that the whole infinity exists at the same time. But you can think of it. You can accept for the time being that this is something, and use it to simplify your mathematical theory or anything, as the case in this picture.
Can I ask one? So, in your talk, you said that we cannot construct real numbers without infinite mechanism. Have you tried to define what is infinite mechanism?
Infinite mechanism is some intuitive idea. It's not very formal or a precise notion, but I think we can understand what it means when we say that infinite mechanism. For example, defining an infinite sequence is an infinite mechanism, or defining an infinite set is an infinite mechanism. Everything that is not finite and unitary way.
Yeah, thanks for the talk. Actually, when I was starting my undergraduate in mathematics, I exactly had the same thought, like real numbers are not numbers, actually. And all my friends were just blaming me, like, oh, are you now crazy?
Yeah.
Now, I sort of understand all the way up to the point where you do the algebraic numbers, right? And then there, up to that point, there's a sense in which these geometrical intuitions are also captured, right? So not only the algebraic intuitions, right? And I'm also very hesitant to go to this conception of line consisting of whatever number of points, right? So at that point, as a student back then, right, I haven't really thought through about this, but I thought the two transcendental numbers seem to be having a very clear geometric meaning, namely pi and e. Right, so what I was thinking back then was maybe adding those transcendental numbers would make some geometric sense, right? And therefore I thought that might be it, that as a number system, having some sort of real, feeling and having the nice connection to this geometric intuition and algebraic intuition as well, it would be like extending the algebraic numbers with two transcendental numbers, e and pi.
Yeah.
So I thought, I'm just curious, I was interested in your response to Ilya's question, like, okay, you want to take the line as primitive rather than consisting of points, and I sort of see the intuition there too. I'm just curious if there would be a way to make sense of that sort of special extension, not just jumping into the real numbers outright, but somehow make it a little more sort of expressive, going beyond, adding a few drops of transcendental numbers, but without going to this paradise of infinite sequences.
I think, for example, consider Q as a set of numbers.
Yeah.
This equation doesn't have any solution in rational numbers.
No.
We can consider a new kind of object, square root of 2,
Yeah.
and add it to the rational numbers,
Yes.
and consider these sets, this new number system.
Yes.
This is again a number system,
Yes.
such that this single equation has a solution.
Yes.
And we can do that, and we can, for example, add another ideal elements to the previous number system and build a new number system such that the equation has a solution, okay?
But
And
if you do that, then you get the algebraic numbers, right?
yes,
Yeah.
algebraic number. You can do that because you can define somehow what is the meaning of y to the 2 equals.
Yeah, exactly.
What is the meaning of y?
Yeah, yeah,
Okay?
yeah.
The number that satisfies this equation.
yeah.
When we want to, for example, add pi
Yes,
to or e to q,
yes,
we need to define pi and e without referring to any kind of abstract and ideal object.
yeah.
We need to define them in Q. And I don't know if we can or not.
No, I don't think you can do that, right?
Mhm.
More of my way of thinking would be to just think of these geometric figures, right?
Uh-huh.
So if you think of the length of a circle,
Mhm.
then pi seems to be extremely natural, for example,
Yeah.
right? And so of course there are some idealizing move there too.
Yeah.
I agree.
Yeah.
But I was just curious, like if one's a finitist mathematician, I thought that might be still
Oh, yeah.
something you might want to be incorporating.
Yeah.
There might be some stark
Yeah.
difference between E and pi too.
Mhm.
But that was just a little comment that I.
Yeah, that's a good suggestion.
I was
What you think?
intrigued by the way, by the Peter's comment saying like start that as a primitive
Yeah.
number system. I mean, I never thought of it that way, but
Yeah.
that was also very wild and exciting project. But yeah, no,
Yeah.
but
Yeah,
was-
that's a good suggestion. We can think about it more. Yeah.
Another thing to think about is that when you're going from the indissolubility of identity to all these things are not finitely
Yeah.
constructible, you're assuming that we cannot finitely, is not allowed to finitely construct the numbers in an undecidable way. So there might be another option in terms of why.
Yes, but I mean, if everything is finite, this is this is an informal idea, actually. If
Yeah.
something is completely finite object, also every aspect of it is decidable.
No,
Yeah.
that's what
Yeah.
you might reject that.
Yeah, we need to add this statement maybe.
Yeah.
Yeah, this is more accurate.
Yeah.
Yeah, thank you. Everything, every construction, every aspect is completely finite and decidable. Yeah.
Any more questions, comments? If not, let's come to